Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. In this episode, we're doing 1-3 reacting masses and volumes. This is going to be part 3 of the IB Chem SL curriculum. Today's we're going to talk about solutions. Let's talk about solutions first. The solvent is going to be the component of the solution in the greatest quantity, and the solute is the component that is going to be dissolved. So here in this example, we have water as our solvent, and this we'll call it Kool-Aid, blue Kool-Aid mix that we're putting in is going to be the solute. This is a bad example because you should never drink out of glassware, and so this is going to be a wasted solution of Kool-Aid. Notice that the common example is going to be a solid and a liquid. We can also have other solutions. We can have a metal-metal solution, which is such as brass. We can have a liquid-liquid solution, such as wine. We can have a gas-liquid solution, and we can also have a gas-gas solution. So different phases of states of matter. Let's talk about concentration. Concentration is moles per decimeter cubed, and you would just take the moles and divide it by the volume to get the concentration. Concentration is also often denoted with square brackets. So here, HCl, the concentration of HCl in, let's say, a solution is 1 mole for every decimeter cubed. Also, if we want to figure out a solution dilution, then we can use the equation C1V1 equals C2V2, where C1 is the initial concentration, V1 is the initial volume, C2 is the final concentration, and V2 is the final volume. Last thing that we're going to talk about is titration. So this is a technique used to determine the exact reacting volumes, usually done several times to get an average. A couple of terms that we need to go over. The equivalence point is the point at which the two solutions have reacted completely. So if you're going to do an acid-base titration, it's when the amount of acid has completely reacted with the amount of base. Now normally we add an indicator to these solutions to help us find the endpoint. Now the endpoint of an indicator is the point at which the color changes. And so a proper indicator must be chosen so that the endpoint matches the equivalence point. So we see here, I think it's in German, this is the only uncopyrighted image I could find, but it shows the various endpoints of various indicators, and so you can strategically choose the indicator that you would like to use based on where you think the equivalence point is going to fall on a pH scale of 0 to 14.
So let's go ahead and do some problems. Explain how you prepare 100 centimeters cubed of a 0.100 molar solution of NaCl. Okay, so we have our concentration, we have our volume, and we need to figure out how much of this we need to add. So we need to figure out the moles of this and then convert it to grams. Let's go ahead and get started. So we know concentration is equal to the number of moles over volume. So their concentration is 0.100 moles over decimeters cubed, and this is equal to going to be our moles. Now our volume, 100 centimeters cubed. We know that there are 1,000 centimeters cubed in a decimeter cubed. So this is going to be 0.1 decimeters cubed. So over 0.1 decimeters cubed. So if we multiply these, 0.1 times 0.1, we get 0.01 equals n. Now that we have moles, 0.01 moles of NaCl, we know that for every 1 mole of NaCl, I think it's 58 grams. So this gives us 0.5844 grams. Okay, so we got to make 100 milliliters or 100 centimeters cubed, same thing, and we got to put about 0.6 grams of NaCl in there. So let's take a look. So here, if you see, we're going to go over first how to not do it, and then I'm going to explain how to do it. So here I have 100 milliliters of, this is just water. I put blue food coloring in there, and my scale just changed. And then we've got 0.6, jumping 0.6 grams about, let's call that 0.6 grams of salt. Here's what you don't want to do. You don't want to fill it up to your volume in the beginning, okay? And here's why. Because when I add the salt into this solution, the salt itself has its own volume. It takes up space. And so when I add salt in there, it's going to raise that volume a little bit past the 100 milliliters. And so that's not what we want to do. You don't want to put the liquid first and then the solute. You want to put the solute first, dissolve it a little bit, and then add it liquid to the mark that you want it. So let's take a look at that. So again, that first way was the incorrect way. This is the correct way. To start with a small amount of our solvent, and then we add our solute in there. Once we add our solute in there, we're going to dissolve the solute as much as we can. And now that we have our solute in there and our solvent, a little bit in, and just enough solvent to dissolve it, now we're going to fill it up to our desired volume. About 100 mils is right there. Okay, so that's how to prepare a solution. All right, next problem. Determine the final concentration of a 75 centimeter cube solution of hydrochloric acid of concentration 0.4 moles per decimeter cubed, which is diluted to a volume of 300. Okay, so this is a concentration 1, volume 1 equals concentration 2, volume 2 problem. So our initial concentration was 0.40 moles per decimeter, and our initial volume was 75 centimeters cubed. This is equal to we're looking for the final concentration, and this is at a volume of 300 centimeters cubed. So we just added some water to this, and we want to see what is our new concentration. A couple of things you'll notice, these are in decimeters and these are in centimeters, but that's okay because the units will cancel out. And so all we have to do is multiply. So we get 0.4 times 75, we get 0. So when we do this math, we get 0.10 moles per decimeter. And that is our final concentration. Since we added more volume, it makes sense that the concentration is going to be less. Okay, so 25 centimeter cubed of 0.1 molar per decimeter sodium hydrogen carbonate, which is baking soda, was titrated with sulfuric acid according to this equation. We have baking soda plus sulfuric acid gives us sodium sulfate plus water plus carbon dioxide. 15.20 centimeters cubed of the acid were needed to neutralize the solution. Calculate the concentration of the acid. So they want us to find the concentration of the acid. The concentration is equal to the moles over the volume. So to figure this out, they've already given us the volume, so we need to figure out the number of moles. Okay. Now they were nice enough to give us the concentration of the baking soda and the volume of the baking soda. So we can figure out the moles. If we take the concentration times the volume, we can figure out the number of moles of baking soda. So let's do this. So we've got 25 centimeters cubed. Let's divide that by 1,000 to change that into decimeters. And we are going to multiply that by 100 moles for every decimeter cubed. Okay, so dividing that by 1,000 changes that to decimeters, so these cancel out. And we should get about 2.5 times 10 to the minus 3 moles. This is moles of baking soda. Again, we're trying to find the concentration of the acid, so this value here. They already gave us the volume of the acid, so we just need to find the moles of acid plug it into this equation. Since we have the moles of baking soda, we can use the balanced chemical equation to figure out a mole ratio to figure out the moles of the acid. So for every 2 moles of sodium bicarbonate of baking soda, that reacts with 1 mole of sulfuric acid, as we can see from the balanced chemical equation. And so this leads us to how many moles of sulfuric acid? If you divide this by 2, we get 1.250 times 10 to the minus 3 moles of sulfuric acid. Now they gave us the volume here. So let's divide this by 15.20. And again, we're going to divide this by 1,000 to turn this into decimeters. Okay. And so the concentration is going to be 0.0822 moles per decimeter cubed. So this was the original concentration of the acid.